this is class 10. This is another repeat problem that we did in class 6 and class 8, where we had, maybe I alluded to it and said that we could do these, but maybe we would come back at a different time. I think I made them into videos because there was a lot of examples and I wanted to make extra examples. So this is actually from my book, so I don't know if I will cover this in class, but this is just a good overall problem to make as a means of comparing the different methods, right? There's only a slight amount of difference here. So I think I don't even think I covered this problem in class for work energy. I think I just went ahead and made it into a video. So here we go. And I don't even have the thing written out. So let me, I'm actually reading from my book right here as I put through the thing. This is lovely, the Dynamics course companion. Try to help you through dynamics is what it's supposed to do. All right, so we got this repeat problem here with the scenarios in scenario A, B, and C. Scenario A, we're just applying a force onto the thing of 50 pounds, but this thing weighs 75 pounds, so it's going to go down. It's just not going to go down as fast as it would if you hadn't been pulling on it. In this other one, we have also 75 pounds. Now we have a weight of 50 pounds. So this is a force of 50 pounds, this is a weight of 50 pounds, and we know already that they're going to go down at a different rate. And then here, we're going to have a larger mass, but the delta between them is the same as the delta between here, right? There's still only 25 pound difference between these two. So we see all these same things from the previous two examples in classes 6 and 8. But now we're going to use impulse and momentum. So we want to make an impulse and momentum triple diagram here. And we could really pretty much just use the same diagram for all of these. Maybe not. Okay, so let's just start out with this diagram right here. We have nothing takes place, right? So this is the initial. And this is the impulse, and this is the final, right? And we're only looking at block A. Let's take in make an XY coordinate axis right here. Nothing happens here, so mass times velocity equals 0, and this is mass of A. And let's say it's this velocity A1 right there. That's good for us. Here we got weight coming down, but times delta T, and then up here we're going to have a force of tension, and then we happen to know the force of tension in this case is going to be equal to P right there, right? Oh, and by the way, let's see, this is an impulse diagram, so we'll say that it's delta T times delta T, right? So that plus that equals this. And then at a later time, we're going to have the mass of A and the velocity A2 right there. And that's in the y direction. It's a simple problem because it's only in one direction. Things are going up in the y right there. So we know that Ft is equal to P, which is going to be 50 pounds. I should have just written that over to the side. What I really want to do is underneath this write out our main equation, right? And by the way, we can make summations right here too. Sometimes I think I should always include that right there because we could have multiple particles coming in here. Okay. And this is like just an aside that we know. Now let's do this only in the y direction, which is obvious right here. So we're going to have 0 right here, and then we'll have positive force times time. So we're going to have that force. I'm going to do this as symbols. No, let's just go ahead and put it in there. 50 times delta T right here. And okay, yeah, let me continue here. And then minus W is 75 times delta T. And that's going to be equal to this mass of the thing, which is going to be 75, sorry. 75. And then, oh, and by the way, that's negative, right? Negative, because it's going to go downwards. So it's 75 divided by 32.2. And we're going to have a velocity that we don't know. So this is going to be velocity of A at 2, and it's unknown. And you see we have two unknowns. Well, here is sort of like a little trick that we're going to do. Let's assume delta T equals 1 second. So, well, how are we going to do that? Well, we'll see in a second. No pun. What the usefulness of this is going to be. We're going to say, well, we know the forces are constant on here. Therefore, the acceleration is going to be constant. So we can find the velocity after 1 second. We can figure out what the acceleration is, right? So let's just assume it happens for 1 second. So what we have now is we're going to have like that 50 times 1 minus 75 times 1. And over here, I'll just keep this as the 7532.2. We could have, here is the velocity. We'll find out the velocity is going to be 10.73 feet per second at t equals 1 second. So now what we could do is we could find the acceleration using kinematics. So we say here is 10.730 plus the acceleration 1 second. The acceleration is obviously going to be 10.73 feet per second squared, right? If you go back and you take a look at the other videos, you'll see that's what we got for that first scenario, for scenario 1. Now if we go and look at scenario 2 now, scenario 2, we have two different things. Now we can actually just reuse all of this. We can actually reuse both of the diagrams, except that the acceleration is going, the velocity is going in the opposite direction for this one. But we still have tension in the original problem up there, right? So what we could do in, we could reuse that diagram, and yes, we could reuse the diagram, or we could write a new one. But we could, let's write out the equation for up here as if it's just ft right here. So this is the equation that we're going to use for the thing. We're going to say that we're going to have 0 plus ft times delta t minus w delta t equals ma va2. Right there. Okay. So, but now we have this new scenario that we're going to have. We want to take another diagram of B, right? So we have the initial, we have the impulse, and then we have the final. And that's just happening to B. So at the beginning, nothing happens, right? mb velocity of B1 equals 0. The impulse onto this thing is now, we're going to have this direction, ft delta t, right? And then, but now we're going to have w, and by the way, this would have been wa right here. So we're going to have wb delta t. That's fine. And it's going to equal, now this is the one that's going to be different right here. We're going to have mb VB2 is now upwards, right? So here is, like, this is going to be equation 1, this is equation 2 right in here. We could still get 0 in the y direction right here. Make sure we know that's just the y direction. We have ft delta t right here, and then minus wb delta t, and then it's going to be equal to a positive, right? Whereas the other one, and then I messed up because that's supposed to be negative right there, right? If we're going back to what this thing is right there, that should have been negative. So okay, now my equation is right, and now we have mb vb2 right in here. So we could plug these things in here. What's going to be easiest to do is let's solve each of these things, right? So ft delta t up above up here is just this delta t minus ma va2 right there, right? And then we're going to have ft delta t down here is going to be wb delta t plus mb vb2. Now just equate those two things with each other, right? And remember that we have a kinematic relation. We have a dependent motion problem here, where we know that the magnitude, at least, of these two have to be equal to each other, right? So we could just replace one with the other, and so we have WA delta T minus MA, and let's solve for VA2, right? So VA2, that's the one we'll have right here, is going to be equal to the weight delta T times plus MB, and then we'll replace that with this right here, VA2, right there. So plug in those numbers in right here. And I actually in here decided to keep these as variables right in here, and I decided to keep them as variables and solve for my velocity, right? So I'm going to solve for the velocity here, and so what I end up saying is VA2 is going to be equal to, and I have WA minus WB and delta T got over the side, divided by MA plus MB. So I stick all those in here, and I see this is 75 minus 50, and I'm going to put in for 1 second, like we'll once again assume delta T is equal to 1 second. What happens for 1 second right over there? And now we're going to have, make sure we put in 75, make sure we put in, this is 75, not 25, 32.2 in there. And what we end up finding is the velocity is 6.44 feet per second. And then once again, we use that same rationale for our acceleration, where we can say now that we're going to have 6.44 equals 0 plus a times our 1 second, so that acceleration is going to be equal to 6.440 feet per second squared, and that's the same thing that we got in the examples that were associated with classes 6 and 8 using Newton's second law and work and energy. And now for the third scenario, one of the reasons why I put this together right here is now the only difference between the second scenario and the third scenario is the amount of weight right in there. So we could just go ahead and use this same equation right here, but instead put in the numbers for the larger weights right here. So we could find that VA2 is now going to be 175 minus 150, okay, and here's our delta T. But now here's the thing that happens on the denominator. What we're going to see is that delta doesn't make any difference, but these masses do. They add together, right? So we have the 175 over 32.2 plus the 150 over 32.2. And so what we end up with is a velocity that's 2.477 feet per second squared. And we know just from like looking right here, we could just say, yeah, we're going to figure out from here with the 1 second assumption that it's going to be 2.477 feet per second squared is what this is, right? So you can see that there's differences between these three scenarios, that they are having more mass makes the thing more sluggish, right? That's the the concept behind this problem, the reason why we put it in there. But also we see that it's this problem is a good one to try to make this comparison between the three methods. And note that we had to do this kind of little sketchy thing, but it worked out, right? The sketchy thing is to assume that it's the delta t was 1 second long, and then we were able to figure out the acceleration, and then based on that 1 second after we found the velocity. So my head is kind of swimming today. I'm not as coherent as I should be, having done an statics exam review session here on a Saturday. But it was a longer video than I intended.